Good morning, my ladies and gentlemen. Good morning, my friends, associates. This is Dr. Mohamed Nezami coming to you again from Jerash, Jordan. Um, I welcome you back. Today, we're going to continue with the part number 4 of this series on design of K band SATCOM low noise block down converter. As you recall, last time we have in this series, I have so far 4 parts, you could say. Um, Here's part 1 through part 3, in which um, I have covered various concepts of this, and so please, for those of you that are just tuning into this part, I urge you to go back and view these 3 parts. Meanwhile, please, if you could sign up to my YouTube channel, I would appreciate it. I have just lost my LinkedIn account for posting an opinions on what's going on in the Middle East. I guess you can't really isolate us from that. And they disabled my account there. Hopefully, if you a lot of you may not be aware of this part because I usually advertise the part completion on my LinkedIn account. So please, if you're watching this and if you like to help send LinkedIn account a complaint for this action on their behalf, which is really disturbance to me because whatever I said was in within the circumference of my freedom of expression according to the American liberty laws and the Jordanian laws as well, even though in Jordan and all of the Middle East, really there are no freedom of expression, unfortunately, but they can arrest you at any time. Okay, well, enough politics. So we're just going to get back. As you recall, I offer my design services for board level designs and system level designs for the fee of $20 an hour. I operate out of Jerash City, Jordan, so I'm much cheaper than operating from the US. I have many clients now in the US, Europe, Middle East, India, um, Malaysia, and they're very happy customers. If you have any designs that you would like to offload your internal design engineers, or just don't have the capabilities of radio frequency and high frequency engineers, are welcome to reach out to me. Consultation for the first several hours is free. I work with you on the concept to drafting requirements and specifications, then on to system architecture, and then finally I will turn in to you fab files, schematics, and BCBs, and so forth, and help you out through the design and development stages, and even continue with the refinement or second iteration of the BCB if there are any issues. Okay, so last time on these 3 parts that I have shown you here, you can refer to these back, okay? And you actually there are 4 parts because one of the third part I split in 2 parts. I covered basically the this proposed dual band Ka band low noise block down converter that has about an IF bandwidth of about 2 gigahertz. Okay. And it spans from 17.2 gigahertz to 21.2 gigahertz, which encompasses both the civilian and military bands as well. Okay. So the hope is that, of course, the specification is I have been using is this here, which is typical from manufacturers of these parts. You can freeze the screen and review them and see them, okay? Now, the design itself was very simple. It's to come in and use basically two image rejection filters, dual filters, okay? Um, the filters are one will cover the low band and one will cover the high band. And then, of course, it will reject the image at these two bands. And then I'm going to use this mimic chip from Analog Devices, which actually it used to be Hittites, for those of you old timers that remember that company that was bought by ADI. And then what I'm going to do, this is an image rejection mixer. So it's a single sideband, low sideband. I would choose it here. This is for the upper sideband here, just tell me it. And then I have an IF section, okay, which uses mimic chips and ceramic filters, okay. The filter in here, I'm going to have to design it. It's a microstrip print filter, and that's the concept for today's session. Let me know. So today, what I'm going to do is, I think, okay, here we go. Okay, so last session, what I've been dwelling on is basically I put this system on system view, selected all the mimic chips and filters, various components, and then brought in or constructed a system model for them, either a small signal model as parameters or a system level parameters model that includes, encompasses both the large signal and the small signal as well. And then, of course, I have my LO section in here, dual LO frequencies I switch in, and dual filters. Now, these are the tasks that I still yet to design. Let me go here. And then what I did, of course, is one of the tasks is to design these filters in here. I still yet to do the other parts, but I picked this stage here for today session. And that's basically what I'm going to do. So I'm going to come in. This is the system on the system view. Okay, and the basically the two filters that I'm going to have to design are these two filters in here. So these two filters right now, from last part, as you recall, they're fifth order Chebyshev, both of them. Um, they're not particularly specified in here at this point. This is system level. So all I did is I gave it the corner frequencies and the order and the insertion loss, and then it constructed those, and that's what I have in here. And if you recall, this system was tested last time, and this is all the requirements and I mean all the performance curves are here shown from last time. So let's see. Okay, this is the system here, the budget link in one of the paths during one of the filters in here, which shows the progression of the desired signal from minus 90 dBm going onward to minus 20 dBm, which is typically what I want into the ground station modem. Okay, and then of course I have the noise figure, which is the gain curve in here. Okay, and I have the gain as well, the cumulative gain in here, which starts out, as you can see, all the way to get to 68 dB, which we're hoping to be around 60 dB once this gets implemented with all the losses that we're going to get through the system. So these two filters in here, basically I'm going to go to ADS. And in ADS, I'm going to specify, oh, I forgot to say, one of the things, of course, before you design this filter, what I did is I actually picked the substrate, okay? And the substrate, it's the Roger 4003. Let me get the data sheet for that, okay? And this is a laminate that basically that I used. It's pretty available, okay? And if you look at the parameters for this, it's the 4003 is right here. the dielectric constant is specified to be 3.38. However, the design parameter is 3.55, okay? And the dielectric dissipation factor or the dielectric loss is 0027 or 0021, depending on the frequency in here. Let's see, we're going to operate it. So 10 gigahertz is that. So this is the substrate. So now they have Mr. Connell, good Connell. He did these experiments on the DK, so you can see 10, 20 gig. We're around here. And if we're using, let's see, I'm going to use 8 mils. We don't have the 8 mil, but 20 mil, we have it here. And you can see all these parameters. Basically, you can review them on the data sheet. So once in ADS, I constructed this microstrip substrate. And then in ADS, they give you this, they call it passive circuit design guide. Okay. And what it is, you can actually come in here and you can design any of these things just simply by putting the requirements. Okay. And for instance, the edge couple filter in here, that's this filter in here. That's what I'm going to design today. I'm putting all the corner frequencies, the pass one, stop one, and so forth, and then the attenuation and the pass band and the stop band impedance, and in the order. Of course, the fifth order because in my system view, that's what I specified. So I have to stick to that. These filters in here are basically fifth order, as you can see in here. And these parameters, I use the same thing as well. So because that's what I'm going to use, I'm going to get the same. Let's see, the conversion gain in here. This is the conversion gain. If I want to get this shape in here and have the same image rejection at the low side band, I have to use exactly the same specifications, and that's what I'm hoping to get out of ADS. So once we get this, all you have to do is you come to design guide and then you go to passive circuits and you get this template that controls this. So you can design it, okay? And then you can simulate, okay? And basically start the iteration on the design process. And here's your filter. As you can see here, this is the filter. And you can come in and check the bands. Of course, this is from 17 to 19, this filter in here for the low band. Okay, so you can come in here and check where this point is at, 17.3. And let's see, the other point is at 19.2. This filter is really good. And the image is, the highest image on this is 15.3. So if we come in here, and if we put it right here, that should be 15.3, okay? Okay, this is 15.3 here. It's 10 to the 10, not 9. Okay, so the image rejection in here is 20 dB, the highest frequency. So once you do this, of course, the filter itself is this one here. You can go down into the filter circuitry and you can push this here, and that's basically what you get in here. You get all the dimensions. So here's the coupled line resonators. There's 5 of them. 1, 2, 3, 4, 5. Okay, and you get the width and the spacing and the length of the resonators. You can see that the length is 100 mils, okay, which resonates at the fractions of a wavelength that we want. However, now, when I did this, one thing you want to notice is that the spacing is 0.362 mil, and that's really impossible to do with printed circuit boards. Um, so, in fact, if you construct the layout of this, okay, this is the layout for this. Let me just get this so I can get. You can see that this resonator in here, because it's only like a half mil, you can't even see it, it's short. And I've tried to I've tried to actually, and you can see the symmetry, of course, the filter. You can see that this section on the left or right of this section, they're exactly the same. Okay. And that's what you see here. So this thing really did not work for me. And what I did, and I reached out to Keysight on this, there are no constraint optimization design guide that you can construct for this. If some of you know, please put down in the comment for me. I would appreciate it. So that's why I was turned to basically to go ahead and what I did is I copied the sorry, let me open that back up. Okay, so instead what I did is I copied this design in here. Okay, even though it's not really appropriate for fabrication. And what I did is I went into the optimizer and actually made the constraint that the spacing in here, this value in here, to be at least 5 mils, because that's really what most BCB houses, some BCB houses even want not less than 6 mils. Okay. So that's what I did, and let's just load that file. Okay, so that's what I did here. So that's the file that I got here. So let's go to the high band, the low band, for instance. This is the low band filter. Okay, and you can see that here it is. Okay, is I set this filter in here, and then I parameterize all the dimensions. Okay, which is the width, the spacing, the length. I parameterize those for from 1 to 5, and I made two additional microstrip lines on either side, just so that it can facilitate the connection to the adjacent. Um, on this side, of course, we have the mimic mixer chip, and on this side, we're going to have, as you recall, the LNA. Okay. So these parameters, and they're basically tuned and optimized. As you can see, that I gave it the range and all that. And I ran this, and of course, uh, I optimized it until I got an appropriate performance. It's pretty difficult to get good return loss on these filters. So for those, some of those of you that have seen this, and then I generated the layout in here. Of course, the layout, when you generate the layout, really it gives you only this section. Okay, but what I did is I added the because the stack layer, of course, in here, I forgot to mention that the stack layer, we have the Roger material, 8 mils, and then we have two conductors on the bottom, on the top, and a via that connects both. And so what I did is I added this copper pore on either side with vias. Okay, these are vias basically. Okay, so you can all right. So, and then of course, I ran the EM on this using the RF Pro on here. Okay. This is a tool that basically uh, Keysight gives you, and this is what we have. We have the bottom ground, okay, plate, and then the this filter itself is right here, and I have these two additional pieces of copper in here. And I simulated this. It takes a sizable amount of time, but I simulated this, and that's basically what I got in here. And you can see that in here. So this filter works nice. It's a little bit different. It has a slope that is like this in Rebel. It could use a little more optimization, but the Rebel is acceptable for me at this point. Okay. Now, notice that the loss is unlike what I had expected, which in higher frequencies you get more loss. In this case, which is better, I want it to be this way because, as you recall from last session, on the system we have seen how the slope is downward for the overall conversion gain, and you can see that. In fact, let's go back here. the converging gain. You can see that the slope is this way, and when I have the attenuation is higher at the lower frequency, that helps me with the IF equalizer so that it's easier. So let's just go ahead and go through these today's session. Let's just finish talking. The other thing that I forgot to mention. Okay, once we're done with that, okay, now I got some discrepancies between the EM performance and the circuit synthesis tool from ADS, and that's when I turned to HFSS. I exported this filter, and I will show you either in a separate part or toward the end. I'll show you how to export from here. Sorry, where's ADS? And yeah, I'll show you how to export this. In fact, let's do it now. So you come in here and you can export this as a whatever format that you want. So what I did is I exported it as an ODB++, and what it does, I do that, and then I import it again into both filters, the low band and the high band, and I got a response from the simulation in here. And let's turn to, for instance, to this one in here. This is one of the filters. This is the high band one. You can see high band. Yes, it's the high band one, and this one was okay. I got little issues on the other filter, which I still need to go back and try to refine it. And that's this one here. This is the low band filter, and I got some issues in here. The issues I suspect mostly is because when you design this based on the S parameter model, you really don't account for all of these. For instance, look at this coupling between these two sections in here because of the width of this here. And so, and of course, things like this, okay, where this here, this resonator, this line in here is actually not being like that. Okay. So we have these issues, and this may have caused the issues. So I'm going to go back and try to troubleshoot this. But once you're done here, of course, you can always go back and export this when you're done to any of these. Sorry, you can go back and, of course, export this to whatever fabrication that you want to do. Like, for instance, Gerber, you can generate Gerber out of this. And the reason we want to do this on this project is because, as you know, so this is, in fact, when you bring this in, when you import it, the stack layer is not the same as ADS's layer. So you have to construct this layer here. So you have to give it the copper width on top, on the bottom, and the Roger material in the middle for it to work, and then simulate it, okay? And then you, of course, you have to specify really the ports here are wave ports on either side. And this is, it takes a while to get this done correctly, because if you don't do this correctly, you really want to do a wave port, not a gap or passive, okay? So anyway, let's get back to this and explain this further, and we'll come back to these. So, all right. So again, what we did is we went into the system view model, and then we implemented this frequency plant low noise block down converter, and this is what you see. We have a SATCOM signal comes in here. There's a LNA. There's a switching between two image rejection filters that are specified in here for the dual bands, and of course two LO fixed LO frequencies, one at 8.125, one at 9.125. And then of course the IF suction is common to both of them. We did this, and as you recall, we did all of this. So this is the filter that was designed in the system view. It was specified like this, and this is the response where the bands overlap a little bit actually. Okay, the IF filters, of course, I picked these filters in here that are ceramic, and they are available from many circuits, Johansson, Murata, and a bunch of other people as well. They come in 50 ohm. So here's a conversion loss and gain, conversion gain, the overall band at all the frequencies in. And we can see the image being rejected, or the image conversion gain is here shown. And we realize the slope in here, of course, we need to equalize that slope at the IF, and we'll do that in the passive LC sections. The noise figure and the overall conversion gain was fully satisfied. And okay. So how to design these two filters? Like I said, I went into advanced ADS and basically to the design guide blocks. And here I chose this block, which is the coupled line edge coupled microstrip filter design. Pick the substrate, of course, Rogers 4003. And then it gave me that, and we saw that we have an issue with the spacing. We couldn't fabricate it, even though the frequency response was really good. So we turned into optimization tool where I took the same exact filter, placed it into a new schematic, and then parameterized this filter in here. Um, let the ADS optimization run on it. And once it ran and converged, I got the artwork. And of course, the frequency response was cool. I tried to do frequency response in um, RF Pro, which is ADS, which mimics HFSS. But really, I got a little disappointing result because what happens is the filter shifted upward. And this is one thing when you're designing printed filters, the shifting is an issue because a lot of times some people who have experienced, that's why a lot of these designers don't depart from the substrate. They stick to one substrate where they learn how the behavior of this substrate as far as a function of frequency. For instance, they would learn accumulate experience that you design your filter 10% off to higher in frequency so that when it shifts back, it's right on frequency. And in this case, it was interesting that the RF Pro, when I simulated this, the filter shifted upward. As you can see here, this is for the low band. It was supposed to start at 17.2, and 17.2 was here on the small signal S parameter model design synthesis tool. You can see in here, and as soon as you do EM on it, in the RF Pro, it shifts upward. Okay, and that's unusual because it usually shifts downward, not upward. Of course, in comparison, this is a comparison here that does my original filter system view is the red one in here, okay, and then the ADS synthesis is the green one, which was acceptable for me, okay, and then the ADS RF Pro is actually this yellowish one, the orange one, and shifted upward. You can see it here where it missed actually the rolled the lower edge of the band rolled on the edge of the skirt. It fell down with a loss that is um, significant. Okay, minus 4 dB in here. Okay. So I went to what I did is I exported this filter despite the fact. So I said, let's just make sure that really what is happening. I can't rely on RF Pro. So I did ANSYS. I exported this filter to ANSYS. And it's exactly the same filter. Okay. And what happened is I got this here, which coincides with the results of the synthesis tool. Okay. So that was interesting. Now, if you overlap all of these filters together, you'll come to realize that the HFSS, which is the red in here, is acceptable, okay, for this filter. So we tried three different ways, okay, HFSS, the synthesis tool, RF Pro, and this one here, System View, which is really based on equations. That's what it does. It evaluates polynomial, Chebyshev polynomial, and it plots the frequency response. Okay, the high band, I did the same thing, so I don't want to bore you with the results, but again, it rolled upwards, so leaving the edge of the band on the edge of the skirt. But when I checked, and then of course I sent it to HFSS, it went at HFSS, and the results were really cool. The return loss was below 10 dB, which is what my target was. So if you compare these, the HFSS, I'm going to use the one from HFS, which is the same as what I started with in. Uh, Now, I forgot to mention one thing. ANSYS has a filter synthesis tool. I think they call it what, Hertz or something. Forgot what it is, but you can refer to that tool, and I did used it before. Although I just prefer to go down this path, which to me it's I'm more familiar with it. So basically, this is what I've got. So what for today's session? So we did these filters. We knocked that off of our agenda. I got to get back and fine tune the low band a little bit, but we'll see how time goes on. And next thing I'm going to do is tackle the probably the LNA part, which involves building this block in here. Okay. So with the time left. Let me get back and just show you because a lot of people may want to see how that is done in here. So this one in here, I want to send this to HFSS, and basically what you do, you can come in here and you basically export it. And the way I export this, I export it with ODB++. Okay, and so I generate this and say yes. Okay, so it did that. What was the name of that? Let me remember what was the name of this. So let me get back and do it again, so that I specify where it goes. Okay, so I'm gonna go back, and then we're gonna export this, and I'm gonna go to the root. Okay, well here it is. It's here. Well, no, let me put it on the root here. I'm gonna say what triple ones. Okay, so basically this. Okay, so let's go back to my root. There it is. So it's on the root. So I'm going to go to HFSS next. Let me close these filters in here. And let me go into import. So basically, I'm going to import an ODE++. And let's go back to here. I'm going to go this one in here. Okay. So I get this template here, and there are three layers, okay? And the outline, I don't want it. So I want conductor one, conductor two, and what these are basically the stack layer, because if you go in here, you've got conductor one and conductor two, okay? And of course, the substrate, it doesn't have that information, but that's what I have in here is basically this filter in here is implemented. There's two layers. There's this layer in here, the bottom, which is the ground, and there is this here, and there are the resonators of this filter. So that's what it's transforming. Okay. So I'm gonna need these two. Okay, and you can look through here and whatever. So let's just say okay. And that's basically what I got. So it's imported, and you can come into view in here and just view it in a solid view. And that's basically what you have in here. Of course, you don't have a Z dimension. You don't have a width right now. It's like DXF. You can import it as DXF as well. And that's where you have to come in really and construct the stack layer. So I'm gonna say zero point 0.7 mil copper here, and I'm going to say 0.7 mil in here. So that does this, and I'm going to add below this layer, another layer, which I'm going to be dielectric, which I'm going to code RO 4003, okay? And I'm going to give it, it's 8 mils, okay? And that should do it. So there, apply it. And then when you go here, of course, it will, you can see that this is here. You can see that the two layers are here, okay, but the dielectric is not really there. So the dielectric is not there because you have to plot it. So I go here and go to this layer, and I'm gonna go to the top. And what I'm gonna do, since I've got the bottom is here, I'm gonna copy that and get it into here, and that basically is my dielectric right now. So when you go in here, you can see that this is 8 mil, well, these are 0.7 mils. Okay, so, and then what you do next is just basically bring up, okay, I'm gonna bring this right on top, okay? If it shifts back and forth, it's not bad. It's okay. So I'm going to go back and make it look like a BC board. So I'm going to put the color in here, like copper this way. And the electric itself, I'm going to put it as a green like this. And the bottom, I'm going to put it like dark brown like this, for instance. And that should be this here, and we're done. So basically now you have a substrate in here that has the bottom copper in here, and the resonators are all on top. Now, next, what you have to do, of course, you really have to configure the stack layer. We have to assign the material. So this is copper, the name, but the material in here, this is copper. This one is copper, but the middle one in here, we have to edit and put the material, and the material is 4003. So you can come in here. These are from the library in ANSYS system, and apply this, and ta-da, we're gone. We're done. So what you do next is, of course, well, the important thing is that we need the vias. We need the vias. This is all ground in here. So what you do in here is you come in here and you drop one via. Now, notice that you want to be consistent with the vias in here. These vias in here are radius of 4 that I created in ADS. So we need, let me get this back to, okay. We need to have this via in here. We need to specify it from conductor 1 to conductor 2, top to bottom. You may want to change these to top and bottom if you want. But let's see, the diameter, whole diameter is 1 millimeter right now. We don't want that. We have our the HFS, the ADS one was 4 mil radius, so that means it's this one should be. Oops, where is it? This one should be 8 mil diameter, because diameter is twice the. Okay, so I've got this, and now if you look at this in 3 dimensions, that's exactly the same width as height as this. Okay, so let's get this. So we select this one here, and I start copying them, basically, and stitching all around this to get and make it like. Let me load it back. Like this one. So what you do is you want to stitch it all around just like this. So once we do that, and then of course, now you can always just look and make sure that the V is stitching both the top and bottom. So once you've done that, you basically want to, all you have to do is just attach ports. And the way to attach ports is really easy. You just basically now, you come into the edge of the copper on one side, and you go like this, just select the edge and select that bottom edge, and then go in and put a port on there, create a port. Of course, the port that you created, you can look back on it, and it's you can specify all the things that you would want to do. And I don't want it as if you zoom out of this, I want the port to extend between the grounds as well. So you can make it as a wave port, okay? And on this case in here, of course, it went off the board. So what you can do is you can reduce the vertical to 4 mils in here, and you bring it back to this, okay? And you do the same thing for the other ones, okay? Well, that's it, ladies and gentlemen. This is Dr. Mohamed Nezami again. What we have to do next is on this. Let's go back here. Is we have to go further and design more of this system, and of course, all the components are picked. The LNA MOSFET devices are picked. And then we have to design this 3 stages, which I will design 1 stage and copy 3 times to get this requirement of 30 dB and sub 1 dB of noise figure. Okay, so if you like to, if you have like again any consulting opportunity, I'm open. I have some bandwidth currently. Please reach out to me. By the way, if anybody wants to have one of these filters, the artwork of any of these filters in here, let me know. I can actually send you the Gerber file and go ahead and fab this if you have a need for it. And I would love to have you share the results with me as well, because all you need to do is just get it. And of course, you need to move this on the side so that you can attach a K connector on this, or 2.5, 3 millimeter connector, high frequency connector. And you can test this, okay? And you can build some through line and open line, and that's the TRL calibration kit for this filter. Okay. All right, ladies and gentlemen. Well, that's it for me, Dr. Mohamed Nezami, with all the greetings and wishing you all a happy Christmas for those in the West and Happy New Year for everyone else. We'll see you in the next session. Thank you very much.